We're continuing on with chapter 22. Today we're going to discuss electric dipoles and lines of charge. So let's go ahead and start with the dipole. On the left side, it's showing you a dipole here. You have a positive and negative charge that creates a dipole. You're going to have a point P, which is some r plus distance away from the positive charge and some r minus distance away from the negative charge. But if you take a point right in the middle of the dipole, right there, it's going to be some z distance away. So we'll just use this axis as our z-axis, as you can see right here. And there's going to be some point P located at the z-axis. Now, at this point, just like when we were calculating electric fields, it's going to have electric field due to every charge. So there's going to be some E positive field that's going to be slightly larger than some E negative field, just because the positive charge is closer to the point. The dipole moment, which is denoted by a lowercase p of the dipole, points from the negative to the positive charge. So the direction of the dipole moment is going to go from our negative to our positive charge. So the dipole moment is going to be the measure of the separation of positive and negative charge. So it's a measure of the separation of charge, or it's the measure of the system's polarity. All right, so we have dipole moment. And that's our measure of the system's polarity. Or separation of charge. Okay. And the equation for dipole moment is going to be lowercase p is equal to qd, where d is a vector and polarity is a vector. So d is just going to show our distance vector between the two charges. And d is the distance between the two charges, as shown right there. Okay. The unit for polarity is going to be coulombs times meters, which makes sense because it's just q times d. So coulombs for charge and meters for distance. Okay, so from symmetry, the electric field E at point P, and also the fields E plus and E minus, due to the separate charges that make up the dipole, must lie along the dipole axis, which we have taken to be the z-axis. From the superposition principle for electric fields, the magnetic field E of the electric field P is, all right, so we're just saying that the electric field is equal to our positive field minus our negative field. And we know that they can't, that they oppose each other, so that's why we have the negative sign in the middle there. So if we go ahead and plug in our equation for electric field, we can start simplifying. All right, so we go ahead and plug in, which is, again, just given as this. It's Q divided by 4 pi epsilon naught r squared. Okay, so we're just plugging that in for each of the e's, the positive and the negative. So the next thing that we want to do is go and get rid of these, because those aren't really in terms of things that we can measure. So we want to really use our z variable and d variable, because those will generally be given in the problem. So the distance between the two charges, and then the distance from the center all the way up to P. Those are the values that we really want to know. So if we go ahead and plug in for R plus Z minus 1/2 D, so if we, again, we take this value here, and to get back to the positive charge, we subtract off 1/2 of D, because this whole thing in between there is D. And then for our negative charge, we want to add 1/2 d, because again, it's going to be this whole distance here, plus this little bit down here, so that would be 1/2 d. Simplifying even more, we can go ahead and try and combine both of these equations, pull out the q divided by 4 pi e naught, and then we're also going to pull out a z squared. So when you pull out a z squared, you end up getting kind of something messy at the bottom here. Continuing on and doing a little algebraic manipulation, you can pull out a 2dz out of there. You want to simplify this a little more and get rid of the 2 and pull the z in down here, so you end up with z cubed and over 2 instead of over 4. Alright, so let's look at this right here. So now we have 1 minus d over 2z squared. Now, if you look at d over 2z, you know it's going to be much less than 1, because d is the distance between the two particles, z is this long distance all the way up here, so you know that d over 2z is going to be pretty small, since d is very small. And because of that, we can just go ahead and say that, well, 1 minus something that's really small, or in comparison to 1, is just going to cancel out. So we can just go ahead and get rid of that. It's going to be so close to 1 that we'll just assume it's 1. Right? So simplifying that, so all you're going to take is this and our d, and you're going to end up with e is equal to 1 over 2 pi epsilon naught qd divided by z cubed. Now, if you remember, this qd over here is going to be our dipole moment. So we can just go ahead and plug that into this equation, and this will be our equation for the electric field of a dipole. Okay, let's go ahead and do an example problem. Okay, so sprites are huge flashes that occur far above a large thunderstorm. They're still not well understood, but are believed to be produced when especially powerful lightning occurs between the ground and the storm clouds, particularly when the lightning transfers a huge amount of negative charge from the ground to the base of the clouds. All right, so if you have negative charge, get negative charge down here, it's this charge transfer up into the clouds. Now, if you notice in C, they kind of give you a visual representation of a simplified way of thinking about this as a dipole. All right, so you have some positive charge here now, which is way underground, some negative charge up here in the sky. And we'll just say, for simplicity's sake, that the H is going to be between both of them. Okay, so we can model the electric field due to the charges in the clouds and the ground by assuming a vertical electric dipole, as shown, that has charge of negative q with cloud height h and then positive q. All right, so let's assume that the charge, that q is equal to 200 coulombs, whether it's positive or negative, and the height is going to be 6 kilometers. Okay, so this is going to be 6 kilometers, and this is going to be, well, this will be negative 200 coulombs, and we have some positive 200 coulombs down here. So what's the magnitude of the dipole's electric field at altitude z1? Okay, so if we had, some altitude way up here, z1 is equal to 30 kilometers, and then the second part, z2 is equal to 60 kilometers, which is somewhat above the stratosphere. What is the electric field going to be? All right. Well, let's go and start with our equation. So, electric field due to a dipole is 1 over 2 pi epsilon naught multiplied by our dipole moment divided by z cubed. Okay, so for the first case, where where z1 is equal to 30 kilometers, plugging everything in, it's 1 over 2 pi epsilon naught times the charge, which is going to be 200 coulombs, times 2 times 6.0 times 10 to the third kilometer. Sorry, I kind of squeezed it in there at the end. So I included the 2 there because it's 2 times the height. The height is given as 6 kilometers, but the distance between the charges is 2 times 6 kilometers, so that's why the 2 is there. All right, this is all divided by z cubed, which is 30 times 10 to the 3 meters, and that's going to be cubed. Okay, so plugging this into a calculator, we see that our electric field is going to be 1.6 times 10 to the 3 newtons per coulomb. Now if I wanted to find the electric field at z is equal to 60 kilometers, use the same equation, so it's 1 over 2 pi epsilon naught, 200 coulombs times 2 times 6.0 times 10 to the 3rd kilometers, and that's all divided by 60 times 10 to the 3 meters cubed. Okay. Plugging that into the calculator, you end up with 2.0 times 10 to the 2nd newtons per coulomb. So you end up with the smaller numbers, which is what we would expect since it's further away. Okay. Okay, so we want to talk about some variables that we're going to be using for charge density. So when we deal with continuous charge distribution, this is kind of moving into the next section. It's most convenient to express the charge on an object as a charge density rather than a total charge on an object. So for a line of charge, for example, if I had, something like a rod, and there was some charge over the entire thing, we would report a linear charge density, or a charge per unit length, lambda. So lambda is used for that. It's some charge per unit length, so we can just say L, whose SI unit is going to be coulombs per meter. So that'll be C over M. So there's other charge densities that we can use. If we had a charge distributed over an area, we would have a surface charge density. So that's given by omega. And so this is omega. And that's going to be a charge over an area. So it would be some charge over an area. And then finally, if we had a volume, we could have a volume charge density, and that's going to be given by rho, which is charge over some volume. Okay. All right, so we're given a ring of uniform positive charge. A differential element of charge occupies a length ds. So if you notice over here, we have this ds, which is just a incremental distance. And then this element sets up an electric field, dE, at point P. So we have some point P, which is a distance away from the ring. Again, we're using our z-axis as our vertical axis here. And the component of dE along the central axis of the ring is dE cosine theta. So we really just kind of want this cosine theta element, because dE is off in this direction. And we'll find out that this, which is, we can just say our perpendicular to the distance of the ring, or the distance away from the ring rather, is going to cancel out, because you have some coming in from this side, some coming in from this side, and this side, and they'll all cancel out. Okay. So we can mentally divide the ring into differential elements of charge that are so small that they're like point charges, and then we can apply the definition to each of them. Next, we can add the electric fields set up at point P by all the differential elements. So if you have differential elements all the way around, they have an electric field, you add them all together, and then you find the electric field at P. So the vector sum of the fields gives us the field set up at P by the ring. All right, so we're letting ds be the arc length of any differential element. So anytime we're talking about arc length, we're going to use s. So ds is going to be a differential arc length. So we have a linear charge density, lambda, is the charge per unit arc length. And the element has a charge of magnitude. Let's see here. So we have dq is equal to lambda ds. Okay. This differential charge sets up a differential electric field, dE at point P, a distance r away from the element. Okay, so r is our distance from the element directly to P, which is shown there. Okay. All right, well, let's first start with our equation for an electric field. So if we had just part of the electric field, we could call that dE, and that would be 1 over 4 pi epsilon naught. And instead of q, we'll just use dq, because it's just a differential element of charge, and that's over r squared. Okay. Getting rid of this dq, let's go ahead and change it to lambda ds. So we can go ahead and change that. So you have 1 over 4 pi epsilon naught, and then the dq just becomes lambda ds divided by r squared. Now, so this r is kind of a problem too. We don't really know. It's not very easy to solve. So we want to change the r as well. And if you look at it, you see this triangle. So you have a triangle that kind of goes up here, and you have this theta angle that's given to us. So if I wanted to represent r in a different way, I can represent it in terms of big R and z, which is the distance from the center all the way to the point. So since r is the hypotenuse, we can just use the Pythagorean theorem and simplify it as such. So we have 1 over 4 pi epsilon naught, lambda ds, okay. And then this is going to be divided by z squared plus r squared. And this isn't to any power because the r is squared, and this value is going to be the square root. So it's going to be z squared plus r squared, and take the square root of that whole thing, but squared again with the 2 there. So it's not going to have any exponent on it in the end. Okay. All right, so this is what we're moving on with right here. Okay. So all of the dE vectors have components parallel and perpendicular to the central axis. So if this z is our central axis, you have parallel components which are going to be going up like this, and then you have these perpendicular components that are going in as such, like I mentioned before. Now the perpendicular components are identical in magnitude but point in different directions. So like I said, those are all going to cancel out. So the only components you really need to worry about are the parallel components. And let's just call that the x direction. Okay, so let's go ahead and one thing we need to think about, so really we have this dE, right? And if we're just worrying about the x components, or the ones that are parallel, we can say it's dE cosine theta. Again, let's go back. Looking at this, if we want the parallel component, we want the cosine component, which is the adjacent component. All right, so if we just take that incremental electric field multiplied by cosine, we run into another problem because theta is another variable that we don't know. We don't really want to worry about having too many of those. So we know that cosine of theta is also equal to adjacent over hypotenuse. And simplifying even more, because again, we don't want that r in there, let's go ahead and change that to z squared plus r squared, and that's going to be to the 1/2. Okay, So now that all of our terms are together, so cosine is going to be equal to all of this, we can plug this back into our full equation for electric field. All right, so dE cosine of theta is going to be equal to, top we have z times lambda divided by 4 pi epsilon naught. And then in the parentheses, you end up with z squared, z squared plus big R squared. And this is going to be to the 3 over 2 now, because we're multiplying in a 1/2, and we already had one. If you look back here, we already had 1 z squared over r, z squared plus r squared, and we're adding in another half by multiplying it in. Now this z here gets displaced on the top there. This whole thing multiplied by ds. Okay. So the next thing that we want to do is go and take the integral. So if you notice here, this is kind of what I had written. So you have dE cosine theta is equal to z lambda divided by 4 pi epsilon naught z squared plus r squared 3 over 2, and then ds. Now z is a constant, which is good. R is a constant. Lambda is going to be a constant. So we can pull all of this outside the integral. And the only thing you have left in the integral for the entire loop, which is 2 pi r. 2 pi r is going to be the circumference of a circle. So you have just the integral from 0 to 2 pi r of ds, which is our incremental arc length. Okay. Now simply solving that integral and simplifying, which all you're really doing is multiplying a 2 pi r on the top, you end up with this as a result. So our electric field, which is our total electric field, even though we just talked about the x component of it with our cosine, we know that's the full electric field because the y component's canceled out. So we can just say E is equal to z times lambda, which is our charge density, 2 pi r, divided by 4 pi epsilon naught, z squared plus r squared, divided by 3 over 2. All right, let's go ahead and do an example. All right, so the figure shows that a plastic rod having a uniformly distributed charge negative q, the charge has been bent in a 120-degree circular arc of radius r. So the whole thing here is 120 degrees. We place coordinate axes such that the axis of symmetry of the rod lies along the x-axis. Okay, so going across, that's going to be our x-axis, and the origin is at the center of the curvature. So if this is a full circle, the very center would be P, where we're trying to find the electric field. So in terms of Q and R, okay, so these are the variables that we're allowed to use, what does the electric field E do to the rod at point P? So it's a negatively charged rod. It's obviously not a particle. Okay. So these x components are going to add, and our job is to add all such components. All right, so again, let's look at the x components here. So if you have just randomly a ds component here and another ds element here, which again is just an incremental arc length, you can see that the x components are going to add, right, in this direction. So you have a negative charge and a positive test charge, you know they're going to attract. So you're going to end up with the electric field to the right. And if you just looked at the y components, here and here, they're going to subtract. Okay. So since this is symmetric, you know that all the y components are going to attract. So you could pick any two DS's on the rod, as long as they're symmetric to each other, and they're going to cancel out. So again, all we really need to worry about is D in the x direction. So let's go ahead and first figure out what our linear charge density is going to be. So again, linear charge density is lambda, and that's going to be just the charge over some unit length. Okay. So our charge is q. It's actually negative q. And our length in this case is going to be 2 pi r divided by 3. 2 pi r divided by 3. So how did I get that? Well, the whole circle would be 2 pi r, because that's the circumference of a circle, and 120 degrees of 360 degrees is 1/3. So that's where the 1/3 comes from. Okay. So the next thing that we can do is go ahead and look at the equation for the electric field. So again, we want to use the same equation. We're using this element dE, 1 over 4 pi epsilon naught, and that's going to be dq over r squared, not r cubed. Okay. Another important relationship that we need to consider is that dq is going to be, our charge density time df. Okay, so we can just go ahead and plug that into the equation. We get dE is equal to 1 over 4 pi epsilon naught times lambda ds over r squared. Okay. Let's go on. Okay, so just like in the other example, our element has a symmetrically located mirror image element, ds, in the bottom half. If we resolve the electric field vectors ds and ds prime into x and y components as shown, we see that their y components cancel because they have equal magnitudes and are in the opposite direction. So again, what we showed here, the y's are going to cancel and the x's are going to add together. We also see that x components have equal magnitudes and in the same direction. Okay, so again, we just need to figure out the x component. So we will again use cosine to get there. So our dEx is going to be EX, is dE cosine theta. And just carrying that through, since we multiplied by cosine theta, we have to go ahead and put a cosine theta on the other side. Okay, ds. Now this sort of runs into a problem, because now you have this ds. Whoops, let me get rid of this one. There shouldn't be two. Now we have a theta and a ds, both of which could change, because the theta changes as we go around the circle, and so does the ds. So we want to kind of eliminate one of them to simplify. Now to do this, we can use the relationship ds is equal to r d theta. Because if you think about it, if you look at just a very small slither of the pie, this is our ds, this is going to be our r, and that is going to be our angle, which is d theta. Okay, so we can see the relationship there. Alright, so let's go ahead and use this, plug it in, so we get rid of the ds. And so dEx is equal to 1 over 4 pi epsilon naught lambda over r squared. Now you have cosine theta r d theta. Get rid of this. Okay, so now everything's in terms of theta. R is a constant, and that's actually going to cancel out. So this one is going to cancel out with one of those. And going ahead and plugging this in, doing a little simplifying, we know that our electric field is going to be the derivative of dEx, which is the derivative of negative 60 degrees to 60 degrees, since the component we can do the integral of is going to be theta now. We'll do from negative 60 to 60, and that's going to be 1 over 4 pi epsilon naught times for r squared cosine theta d theta. All right, so we want to pull everything out that we don't need from the integral. So that's going to be our lambda over 4 pi epsilon naught r. And I think we got rid of one of those r's. Yeah, let me take that out. We just have one r on the bottom now. And now we can put the rest inside the integral since it has to do with theta, some theta, d theta. Okay. This is all equal to, again, lambda over 4 pi epsilon naught r, and the integral of cosine theta is just sine theta, so you get sine theta between 60 degrees, negative 60 degrees and 60 degrees. Oops, sorry, keep jumping. Okay, so now you can just go ahead and plug in negative 60 and 60, which is going to be equal to lambda 4 pi epsilon naught r sine of 60 degrees minus the sine of negative 60 degrees. And plugging everything in, we go ahead and get a number, which is 173 times our charge density divided by 4 pi, epsilon naught times r. Now, going back to the beginning, we can go ahead and plug in for our charge density here. So we found that our charge density was going to be q over 2 pi r divided by 3. Plugging that in and getting, let's see, so that would be 1.73, numerically 0.477 q divided by r divided by 4 pi epsilon naught r. And finally, you end up with 0.83 q divided by 4 pi epsilon naught r squared. And that's going to be equal to our electric field. And there you have it. In the next lecture, we're going to be discussing a charge distributed over a disk.